All right. So, looking at our reminders and things coming up. You have mastering due tonight, and you have mastering due Friday. We'll do a group quiz on Friday, and your third exam is 2 weeks from today. Your final exam is May 1st. So we're in our last, maybe 11 or 12 lectures. We're almost done. I should look ahead. We're almost done. You only have like 12 lectures left, tops. Maybe less than that. You should have lab this week. No lab next week. This week is just regular. Next week there's the student symposium on Tuesday, which messes up all the lab sections. I will double check that. I know for sure there's no lab on Tuesday, because all classes are canceled on Tuesday, the 14th. Yeah, the student symposium's on the 14th. There's no classes. I have no idea. I don't teach the lab, so I'm not up on it. Alright, so today we're going to scoot through the last little bit of Chapter 17, which is how we combine S's and H's and G's and K. Alright, so this is like the last thought we had on last Wednesday, right, where the entropy of the substance depends on its state, where the entropy of a liquid is going to be less than the entropy of a gas. So when you, the only reason I bring this up is when you go to do the mastering homework, make sure you pay attention to what state of matter they are looking at, because they have different entropies. So you can't just go and look up water. You got to look up liquid water or gaseous water, solid, whatever it is. You have to look it up using the right state of matter. So the question is, how do we calculate delta S of a reaction? We do it just like we do delta H, right? So the delta S standard state of a reaction is the sum of all the entropies of all the products minus the sum of all the entropies of all the reactants. What's this little n mean? You remember moles. So this is that's the stoichiometric amount, right? So that's the big number in front of whatever molecule you're looking at. And as you're thinking about entropies, keep in mind that standard state entropies are always non-zero at room temperature. What temperature do I have to be at to get my entropy to be 0? 0 degrees Kelvin. And since we're not there, they'll have to have a non-zero value. So if you're starting to plug in your entropies and you're plugging in zeros, you are looking at the wrong column in your appendix. You're looking at H's. Move one over to S. S always has a value. So, let's do a practice problem where we put into practice our brand new super exciting equation. So let's compute the delta S of reaction for the following chemical equation. Alright, so these are S's that I looked up in the back of the book. Now I want to figure out the overall delta S of the reaction. Right, so that's my equation. Sum of the stoichiometric coefficient of all the products minus sum of the stoichiometric of the reactants. I turned blue there for a second. Alright, so what compounds are my products? Okay. How many nitrogen monoxides do I have? 4. So we're going to do 4 times 210.8. And then how many waters do I have? 6. Minus. Okay, how many ammonias do I have? 4. Right, everybody's thinking so hard and writing this down you can't answer me at the same time. And then I have 5 oxygens. And that's it. We just need to do a calculation to figure that out. How many significant figures do I get from just this parentheses right here? 4, right? Because that's an exact number, so it doesn't count. So I get 4. So then if I add these together, how many decimal points do I get? 1. 1 decimal point, right? Because it's all, if you're multiplying, and just 1 decimal point if you're adding together. Okay. And over here I have 4 and 4. So that part together would be since I added, I get the decimal point rather than multiplication. I'm sure you guys all remember significant figure rules, so that's good. If not, there's plenty of time to catch up on them. Oops, no. Alright, so 1976, 17.7.2. What are the units of this? What does this number represent? And which has units of moles. So what are my final units in? Joules per Kelvin. JK. Jokes per Kelvin. Alright, do you want to do another one of those, or do you feel fairly confident in multiplying in addition? Good. Okay. If you want to do another one, the next slide is another problem. If you have your slides, I'll go ahead and tell you. You can double check your work later. So if you want to check your work later, that is the answer to that one. If it has a negative entropy, what's that tell me about the spontaneity of this particular reaction? It is unlikely to be spontaneous. What's the other thing that tells you it's unlikely to be spontaneous, just looking at the chemical equation? How many moles did I put in? How many did I get out? 4, right? So that should be double checking your work. So if I put in 5 moles and I really got 4, I should have a negative delta S. Good, okay. Let's move on and talk about G. There's usually a funny little song I play at this point, but you guys are too young, you wouldn't know about it, so never mind. Original Snoop Dogg. Which, when he's singing about G things. These would be G things. It's nothing but a G thing. Right? Now you guys can see me stuck in your head. Alright, so free energy changes. We're going to talk about how to calculate a change in Gibbs free energy if we know changes in entropy and changes in enthalpy. Alright, so now I can calculate the change in delta G if I know the changes in entropy, changes in enthalpy at a given temperature. Alright, so we can calculate the change in the standard state Gibbs free energy using the change in enthalpy and the change in entropy as long as we are at a given temperature. So that seems pretty exciting, so we should go ahead and do that. I'll wait till everybody has that all written down. Alright, so let's calculate the delta G. Okay. We're going to have to do it in 3 parts. Right? So here's my table of data. I went to the back of the, these shouldn't be deltas, they should be just plain H's for finding deltas. Alright, so I went to the back of the book and I looked up standard state entropies and standard state enthalpies for this reaction. To use my equation, I have to find the change in enthalpy and the change in entropy. So part A, we're going to find the delta H. Part B, find the delta S. Part C, put it all together. Right? Alright. Alright, so to find the change in enthalpy, it is equal to what? We just did it, but we called it S. Okay, whew, tough crowd today. Okay. Alright, it's the same thing. It's going to be sum of all the H's of the products minus sum of all the H's of the reactants, each raised their stoichiometric coefficient. Alright, so if I want to find the delta H standard state of reaction, what is my product? SO3, and how many of them are there? 2, okay. Whew. Alright, and then I have 2 products where I have 2 SO2s. 2 times negative 296.8. Why is this a 0? Why is it's a naturally occurring element. It is in its standard state, which means it has no enthalpy. Right? Oxygen is normally found as a gas at 25 degrees Celsius. So that's why that's a 0. Alright, so we just need to solve this. So 2 times negative 3.567 minus 2 times negative 2.6. What unit am I in? Just kilojoules. It's a negative delta H, so is this exothermic, endothermic? Exothermic, okay? Looking at my reaction, what sign should my delta S probably have? Negative, right? Because I'm putting in 3 gases and getting out only 2 gases. Alright, let's prove that. Let's find the delta S. So why are none of these S values 0? Because we're at room temperature, right? We're at room temperature, so they all have some sort of entropy. Plus they're gases. They definitely will have some sort of entropy. Alright, so let's see. We do 2 times 256.8 minus 2 times 248.2 plus 205.2. Yeah, otherwise I'd run out of space. what are the units of my entropy then? Joules per Kelvin, okay? Alright, so now we need to put it all together and find my delta G. Alright, first thing to figure out how to plug them in, what's one issue I have before I can plug them in? There's two issues, so what's one of them? Units, right? This one's in kilojoules and this one's in joules. Do you care which way we go? Okay, I'm going to pick joules, because I think that's easier. What's the other issue I'm going to have right now? Temperature. What temperature do I need to be in? Kelvin. What temperature do they give me? Celsius. So how do I get from Celsius to Kelvin? 2 times 3. Alright, so I got 298 Kelvin times -188 joules per Kelvin. Alright, now we are sorted. Few questions. One, does the delta S sign make sense with the equation that you were given? It does. Good. Is this overall reaction spontaneous or non-spontaneous? How do you know it's spontaneous? Right, the negative delta G. So even though you had a bad entropy, you have a gigantic enthalpy, right? That's way, way bigger. So the enthalpy overcomes the bad entropy. Spontaneous. Question? Because that's oxygen at 25 degrees Celsius, I would expect the oxygen to be a gas. And if that's what I expect, then it's a 0. Right? There's no entropy. Yeah. Yes. If delta G is negative, spontaneous. So even though the entropy is bad, the enthalpy is so much bigger, it overcomes the bad entropy. So, follow-up question to that. What if I change the temperature? So, what if I change the temperature from 25 degrees to 125 degrees Celsius? Does that change the delta H? It shouldn't. Delta H won't change. Delta G will, right? So delta G 0 reaction equals delta H 0 reaction minus delta. All right. Do the delta H or delta T or delta H or delta H? SH. Do the deltas change? These guys. Now, what's the only thing that's changed? Temperature. So we can plug in the values we just had. Wherever I just put them. There they are. Because it's temperature independent. So all I've done is I've warmed up the whole reaction to see what happens to my delta G. Alright, so now my new temperature is 125 plus 233. Yeah, all I did was I just warmed it up. Oh, let's see. Did I get it right? No, I didn't. B1. Alright, so I was at 298 and now I'm at 398. Is my reaction still spontaneous? Okay. Is it more or less spontaneous than at room temperature? It is less spontaneous. Right, so I was at 1.42, now I'm at 1.23. So by increasing the temperature, what has a stronger effect? The entropy, right? And we have bad entropy, so by making it hotter, we've only made the entropy worse, which makes the overall reaction less spontaneous. Sure. Question first? Mm-hmm. That would be too much. Yeah, it'll always just be whatever's on the table. Yeah. Okay, right, so I was spontaneous at 298. I went up to 398. 398 affects the entropy, and I have bad entropy. So by making it hotter, I only make the entropy worse, which makes the overall spontaneity decrease. All right. What do I have? Questions anymore on that? Plugging it in, rolling around. Yeah, question.
If we have low temperature, would it have made it better than
Mm-hmm. Yep. Yes, if I went colder, it would have helped more. Yeah. Mm-hmm. And in fact, there could be a point where I heat it up so much that it's no longer spontaneous. You could keep, right, if I increased this temperature by so, it would be bajillions of degrees. But there'd be a point at which it would no longer be spontaneous. Alright, so since delta G, standard state reaction, is a change in the free energy, and free energy is a state function. Free, there's no fee. Free energy. We can solve for delta G just like we did for delta H and delta S. That equation should look super familiar because we've used it 3 different times now. So, it's definitely an equation you'd be able to do, right? It's the same equation. Either I'm looking for S's or H's or G's. It's just a state function. So again, just like for enthalpy, elements in their standard state have a Gibbs free energy of 0. So, new equation, what should we do next? Try it out, make sure we can operate it. And lucky for you, it's the exact same kind of problems we've been doing for like 20 minutes now. So you should be super good at this by the end of class. Alright, so let's use standard free energies of formation to determine the overall delta G of this reaction at 25 degrees Celsius. Alright. So again, you'd go to your table in the back of the book, or provided table, and look up the G's, and then just plug them in. Alright. I'll probably give it to you as a table, just because it's easier to look at in a table. I think for the homework, you have to either have your textbook with you, or use the online textbook to go to the appendix to find it. Yes. Yeah, the online textbook has it all in it. So, yeah. Alright. So, again, either write small or write on 2 lines, because we can't fit it all on here, right? So, products, I have 1 carbon dioxide. I have 2 waters. And I have 4, does anyone know this molecule? Ozone. Minus. And again, why is oxygen 0 in this case? Because at standard state at 25 degrees Celsius, we would expect oxygen to be 0. So it doesn't even factor in. Alright, somebody's have to do that top. Let's see what that is. Let me see. Let me get 394.4. What are my units? Kilojoules. Is this reaction spontaneous as written? Yes. That's all there is to it. So obviously the delta G is the easiest one to figure out if I give you a table of G's. I'd say the key to these questions are going to be, what did I give you a table of? Right, if I gave you a table of G's, do it this way. If I gave you a table of H's and S's, you're probably going to see the other one. As a smart scientist solving the problem. Read the information I gave you and then use the appropriate equation to plug all that stuff into. Any questions on that? No? Okay. It's pretty much just the same thing over and over and over again. Alright, so. What if I now have a series of reactions and I don't know the delta G for them? And I realize the sentence makes no sense as written. To determine the delta G for a series, we use the same rules we use with delta G. That makes no sense. Okay, what I meant was delta H. Otherwise, that's a circular argument and you're not getting anywhere. So to determine the delta G standard state reaction for a series, use the same rules you did when we had delta H's, which are different rules than K. Right, when I had a series of K equations, if I reversed it, it was 1 over. If I multiplied, I put it to the power. Those are K's. Those are not these rules. G's and H's are much more straightforward. If multiplied, then multiply. If reversed, then change the sign. So they're the easier series of things to do. Whatever you did to the reaction, you do to the H. That's a state function. Alright, so K was not a state function, it's a fraction of ratios. So if you're looking at K's and trying to add them all up, if you reversed it, then you flip the fraction, which is what the 1 over is. But these are all state functions. So if I multiply, you can multiply. If you reverse it, you just change the sign. So, what if I have a question like this, which, I don't know what I was doing when I typed these. Another incomplete thought. Determine the delta G of the following reaction. Not given. The equation I meant to give you was this, right? That's all the information, but I have to give the equation I want to get to. Alright, that's the equation I want. And I don't have all the information to do that. But I have all this other information about other reactions that could add up to make this one. If I give you a bunch of delta G's in a series of reactions, I want you to do this. If I give you an equation and a table of delta G's, what should you do? The product must the reactants. Again, so by the different kinds of information I give you should tell you what you should do with it. So if I give you something like this, I want you to add them all up to make the equation I want. Alright, so thoughts begin. That's the best place to go. Alright, we'll look at the product. Alright, which, no, that's not any good. Alright, we'll look at this. N2O. Which, I guess I'll number them. Which equation has N2O in it? Number 3 has N2O, right? Is it on the correct side of the arrow? For start. Okay. So for now, we'll just rewrite it and leave it alone. All right. Let's look at the NO2. Which reaction has NO2 in it? Number 1, is it on the correct side of the arrow? No. So what do I need to do to it? Flip it over, then what do I do to the delta G? Change the sign. All right. Alright, so then that leaves us with equation number 2. It has NO as its product. Is the NO on the correct side of the arrow? Yes. Okay, so we'll just rewrite that one as is for now. Alright, if I added them up together right this second, would I have the correct equation, final equation? No. What is something that appears in these reactions that doesn't appear up here? The O2 and what else? N2. How many O2s do I have as products? 2, right? How many N2s do I have as products? As of right now, on this side, right? I have 2, and I have 2. I want those to cancel out, so what do I need to do to this third equation? Multiply the whole thing by 2. Maybe I should pick the bolder color. 2, 2. Alright, so if I do that, do all the N2's cancel out? If I do that, do all the O2's cancel out? Okay. If I look at what I'm left with, I have 2N2O plus 2NO2 arrow 6NO. See what that is right now. Negative 207.4 plus 71.2 plus 75.2 times 2. Alright, is that the equation I want right now? Is that the final equation I need? No. How am I off from what I want? I divide the whole thing by 2, right? If I do that, 3, what do I need to do my delta G? Divided by 2. So the equation I wanted that's as tricky as they come. And you've seen that before, right? We did that with H's before. We've done something similar with K's. So, the strategy of solving is going to be the same problem. Questions on this before I come to the last section? Except what? I was gone before? Let's see the slide number. 35. Oh, there it is. Alright. So you may be thinking, man, this is fascinating. I wonder how it relates to chapter 14, 15, 16. That's a glad you asked. How does G relate to K relate to Le Chatelier's? All great questions. So, right, K is our equilibrium constant. So how does K relate to delta G? Let me write this up here just in case, perchance, you have forgotten. Right, talking about which direction the reaction is currently going, product favored, reactant favored, equilibrium constant. Alright, so delta G is the increase or decrease in free energy as we go from reactants to products, right? We're looking at the total sum of free energy. But reactants are not always completely converted to products, right? When we think about that, you never have a reactant concentration at 0. That'd be a 0 on the bottom of your fraction, which is catastrophe, right? So there's always some reactants left over during your reaction. So even though you have a product-favored reaction, there has to be reactants left in that, right? Because K doesn't measure the concentration of products. However, the concentration of reactants is simplified. That doesn't look like anything. Product of reactants, right? Their concentrations. And so, you can't have 0 reactants. That doesn't make any mathematical sense. There's always going to be some reactants left over. So how do we relate that to the sign of delta G? Alright, so you have your reactants being mixed. They're going to proceed to position of lowest, man, I've got the F. Really sorry about that. Okay, lowest free energy, which is at which point they're going to reach their equilibrium concentrations. So in order to figure out where we are in terms of equilibrium, we're going to look at this new equation. Alright, so let's take a little tour of the new equation. If I'm delta G with a little 0, what kind of G is that? Standard state, what's R? Gas constant, T is temperature, what's Q? The reactant coefficient, right? And Q, in case you have not looked at it lately, right, it's the concentration of products, each raised to the stoichiometric coefficient, over reactants, each raised to the stoichiometric coefficient. At what point of the reaction is Q? Anywhere but equilibrium. So this is a measure of where you are compared to equilibrium. Right? Alright, so this will tell us where we are compared to equilibrium and what the reaction has to do to get to equilibrium. Alright, so if I'm at equilibrium, this delta G, not standard state, is equal to 0. So if this is equal to 0, I can rearrange this equation. Right, if it's now equal to 0. What does Q turn into if I'm at equilibrium? So this is anywhere but equilibrium. This is when I'm at equilibrium. So these two equations tell us, okay, if I have a delta G that's negative, what does that tell me about the reaction? Okay. If I have a delta G reaction that's negative, which means spontaneous, if this value here is less than 0, right, if this side of the equation is negative, what does the ln of K value have to be to keep it this side negative? Right, so the ln of K has to be positive, which means that K has to be greater than 1. Is this? Alright, so for this to be true, for this to be negative, ln of k has to be greater than 0, which means that k by itself has to be greater than 1. If k is greater than 1, what sort of favored reaction is that? Product favored. Which should make sense, right? If it's spontaneous, you are telling me in words that's likely to go to product. So the k value should also tell me likely to go to product favored. So they should be telling you the same information, just depends on which side of the equation you're looking at, k or g. Okay, what if I have a delta G reaction that's positive? What's the value of k going to be compared to 1? Alright, less than 1. Which again should make sense. This is non-spontaneous. Which means it's reactant favor. Which means it's unlikely to make products. Same thing. Telling you two things about the same thing. Alright, so because I'm a picture person, we'll look at a picture. Alright, so here we are looking at a reaction where I have only reactants compared to only products, right? And my reaction is going reactant to product. If I'm at a point that Q is less than K, it means I have lots and lots of reactants and not enough products. We're going to start moving this direction. Right, if I'm the opposite side, if I have Q greater than K, I have too many reactants, it's going to come back. I'm at equilibrium when they're equal. Why is my delta G, I guess, what sign is my delta G? Negative, right? Because at the beginning, it was high and now it's low. So overall, that's a negative delta G, that change. Which means it's likely to go towards products. This is what you're looking at here, right? Likely to go towards products, but I can't make all products, because then I wouldn't have any reactants left. So, Q, K, G, H, and S all tell me where I am on my thing. We have one more letter we're going to throw in there. We have some E's coming up here in a little bit. But, combining all those thoughts together, the free energy at equilibrium is lower than the free energy of either the reactants or the products. Right? Looking at this picture. Equilibrium is less energy than either product or reactants by itself. Delta G, standard state reaction, tells you the energy at equilibrium, because that's where it's equal to K. And then delta G tells you which direction the reaction is going. It's going towards products, or towards reactants, or somewhere in between. See if I have any last things to add. I said like one more picture, which you can look at on your own. That compares K to Q, the free energy, everything all together. So that's the end of 17. On Wednesday, we'll start electrochemistry and compare E to Q to K to H to S. I'm excited. It's my favorite chapter. I wait all year for the electrochemistry chapter.